Hello and welcome. My name is Aaliyah Strand, and today I will be presenting on a compensating control for systems with intermittent actuator faults. First, I will begin with a brief overview of today's presentation. I will begin by briefly describing the motivation for this work. Then, the significant results will be discussed, beginning with a brief review of the modified Kalman filter, or MKF, for systems with intermittent actuator faults and extension to systems with unknown fault rates using multiple model estimation, or MME. After a discussion of the proposed compensation control and its theoretical development, I will discuss its simulation verification using a DC motor with intermittent actuator faults of different rates. Finally, I will present a summary of the work as well as avenues for future work on this topic. The motivation of this work stems from the fact that actuators can be susceptible to random intermittent faults and many different failure modes. These faults and failures may become more common with the increase in wirelessly networked and cooperative systems. Early work involving actuator faults tended to focus primarily on the identification of the failure mode during operation. Isolation of the failing actuator and the mode of failure were common topics of interest. More recent developments in the literature focus on the control of systems with actuators experiencing different types of failure modes, such as reduced effectiveness failures, where the actuator is not capable of applying the full range of input values. A few works address the control of systems with intermittent actuator faults, but only the case where the fault statistics are known is considered. This work proposes an intermittent actuator fault compensation method that can be used in the case where the actuator fault statistics are unknown. First, I will discuss simultaneous actuator fault rate identification and state estimation. Consider a state space system of the form of 1, where xk is the state vector, yk is the measurement vector, and vk and wk are the Gaussian distributed system and measurement noise. Here, the intermittent actuator faults are modeled as a Bernoulli random variable gamma k, which has a value of 1 with probability xi, or the success rate, and a value of 0 with probability 1 minus xi, or the fault rate. Gamma k multiplies the input vector uk, indicating that at any time instant where gamma k is 1, the commanded input is applied as expected. Similarly, for any time instant where gamma k is 0, the actuator's fault, and the commanded input is not applied to the system. The success rate of the actuator xi is bounded by 0, corresponding to complete failure of the actuator, and 1, corresponding to a system with no actuator faults. The Kalman filter can be modified for the system given in 1 if the success rate of the actuator is known, where the state estimator is given by 4, and the optimal gain and error covariance by 5 and 6. We can then extend this modified Kalman filter to unknown actuator success rates using the multiple model estimation algorithm. To extend the modified Kalman filter to the case where the success rate is unknown, we can consider an algorithm commonly referred to as multiple model estimation. In MME, we have an unknown parameter xi, which is constant or slowly varying, for which we have lower and upper bounds. We then design n filters around n possible values or hypotheses of xi. These filters operate in parallel using the set of measurements to generate state estimates dependent on the hypothesized values of xi. Then, the most likely value of xi is determined using Bayes' rule. By expanding Bayes' rule, we can calculate the posterior probabilities recursively, where this term is the previous value of the posterior. Here, P represents a probability density function, xi is the ith hypothesis of the unknown parameter, n is the number of hypotheses, lowercase yk is the measurement vector at time k, and capital YK is the set of all measurements up to time k. To simplify the calculation of 7, we can assume Gaussian distributions as in 8. Here, the small p is the dimension of the measurement vector yk, tilde yk conditioned on xi represents the innovations sequence for the ith filter, given by 9, and omega k conditioned on xi is the second moment of the innovations sequence of the ith filter, given by 10. Using the resulting estimate of the success rate ThA, we propose a control that compensates for the intermittent actuator faults. The proposed control takes a probabilistic approach to maintain the mean value of the equivalent healthy system and is given by 14, where UK does is the desired control of the healthy system, and ThA hat k is the estimate of ThA at time k. Since we are taking a probabilistic approach towards the control, we consider the progression of the mean and the covariance of the system states, both in the case of a system with a healthy actuator and in the case of a system with actuator faults using the compensation control. Here we see that the mean of the healthy system is given by 15, and the mean of the system with actuator faults and fault compensation is given by 16. Note that as ThA hat approaches ThA, the mean of the compensated system approaches that of the healthy system. This can be achieved using the MKF with MME through proper selection and refinement of the hypothesis set during operation. We have shown that when ThA hat approaches ThA, the proposed compensation control maintains the mean value of the healthy system in the presence of intermittent actuator faults. Next, we consider the progression of the covariance of the system states. The covariance of the healthy system, where ThA equals 1, is given by 19. The covariance of the system with intermittent actuator faults using the compensation control can be expressed as in 22 when ThA hat approaches ThA. From these expressions, we see that for ThA less than 1, 22 is larger than 19. As ThA approaches 1, however, 22 also approaches 19. Based on these analyses, we see that when the estimate of ThA approaches its true value, the compensation control can maintain the mean value of the healthy states, though the covariance of the states increases dependent on the value of ThA. To verify the performance of the proposed compensation control, a per-unitized DC motor with intermittent actuator faults is simulated. The simulations are performed for several different values of ThA which are unknown to the estimator. As an initial verification, only open-loop control is considered. Other closed-loop controls will be considered in future work. The discretized per-unit DC motor model is given in 23, where x1 is the phase current, x2 is the rotational speed, and UK is the commanded terminal voltage. The rotational speed and the voltage applied to the motor terminals are measured as shown in 24 and 25. 5 filters are used in the MME algorithm, each designed around one of 5 hypothesis values given in 28. This hypothesis set uniformly discretizes the region between 0.5 and 0.9, but other hypothesis sets may be selected or refined during operation as needed. Success rates both within and outside the hypothesis set are simulated to verify the performance of the proposed control more effectively. Here we have some representative plots of the posterior probabilities for 2 different actuator success rates, ThA equals 0.8 and ThA equals 0.87. Note that when ThA equals 0.8, the posterior probability corresponding to the hypothesis that ThA equals 0.8 approaches 1, while all other posterior probabilities approach 0. This indicates that the MKF using MME correctly identifies the actuator success rate. In addition, when ThA equals 0.87, the posterior probability corresponding to the hypothesis that ThA equals 0.9 approaches 1, while all other posterior probabilities approach 0. This demonstrates that when the true value of the unknown parameter is not within the hypothesis set, the MME algorithm converges to the closest hypothesis. In such a case, the hypothesis set can be refined during operation using the previous convergence point to achieve a more accurate parameter estimate. The 2 remaining figures, on the right, compare the progression of the states of the healthy system in blue and the states of the system using the proposed compensation control when ThA equals 0.8 in red. Note that despite the actuator failing to apply the input 20% of the time, the system states tend to track the healthy states fairly well when the compensation control is used. Table 1 presents a summary of the average percent differences between the states of the healthy system and the system using the proposed compensation control over 50 simulations. In general, when ThA is within the hypothesis set, the percent difference is quite low, indicating that the compensation control is functioning as intended. When ThA is not within the hypothesis set, as when ThA equals 0.83 and ThA equals 0.87, the percent difference increases slightly due to the small bias in the estimate caused by the selection of the hypothesis set. This difference can be reduced by refining the hypothesis set during operation. Table 2 presents a summary of the average variance from the healthy system when using the proposed compensation control over 50 simulations. The variance of the compensated system from the healthy system is calculated using 29, where xdiff is the difference between the healthy system state and the system state when using the compensation control, and kend is the length of the simulation window. The variance is used to help quantify how much the compensated system strays from the behavior of the healthy system. As expected, the variance tends to decrease as the value of ThA increases. In this presentation, I discussed a proposed compensation control for systems with intermittent actuator faults with an unknown fault rate. This technique builds upon the modified Kalman filter using MME for identifying the fault rate of the actuator and takes a probabilistic approach to the control. In particular, the compensation control maintains the desired mean value of the system states when the estimated fault rate approaches the true fault rate. The operation of the proposed compensation technique was verified through the simulation of a DC motor for several actuator fault rates, and it was observed that the technique maintains the desired mean value of the states while slightly increasing the variance from the healthy states. To wrap up, I will briefly address some avenues to extend this work in the future. In this work, only one hypothesis set was considered. Future investigations can address the influence of the hypothesis set on estimation and control. In particular, refining the hypothesis set during operation for more accurate control should be considered. The use of various closed-loop control techniques, including state estimate feedback, will also be investigated. This concludes my presentation. Thank you for your time.